I am Anil Kumar. Welcome to my series on logarithms. We'll consider important properties and laws of logarithms in this particular video. I'll prove all the properties and laws of logarithms also. So let's begin with the very basics. The graph which you see here is showing graph of exponential function in green, which is always increasing. That means the base is positive. A line which is y equals to x, and then a reflection of the graph of exponential function on the line to get the inverse function, the logarithmic function. Correct. So the red graph here is that of the logarithmic function. So exponential function is basically y equals to a to the power of x, where a is greater than 0 and a is not equal to 1. If a is 1, you get a constant line y equals to 1, which is not always increasing, and that is not an exponential function. And that is why we have the restriction that a should not be equal to 1. Hope that makes sense. Now, logarithmic function is, as you know, inverse of exponential function. To get the logarithmic function, we actually reflect it on the line y equals to x. So on the graph given here, the orange line here is represented by the equation y equals to x. The green line here is a to the power of x, and the red line here is log to the base a of x. Is that clear to you? Right. So these are the different graphs for the lines. Now, when we talk about logarithmic function, we could also write the inverse by flipping x and y. So in this particular equation, if I write x instead of y and y instead of x, what I get is a to the power of y is equal to x, and that becomes the inverse of a function. And again, the restriction will remain that a is not equal to 0 and a is not equal to 1. A is greater than 0 and a is not equal to 1. And log to the base a of x is y, right? So the same equation has been represented in the inverse form. Now here are a few properties which is kind of a reference for you to look at. Here I've compiled all the properties and laws, and this page could be kind of a formula sheet or a summary sheet for you. We'll now take one by one each element on this particular slide and then describe or understand it. So let's begin with understanding the graph first, where we'll talk about domain and range. Now, as I was saying, the graph in green is basically y equals to a to the power of x. So that is this exponential graph. Now, for exponential graph, we know that the domain is what? Domain is all the values of x. X belongs to real numbers. X can have any value. However, the range of the function is that the y values are also belonging to real numbers, but y values are always greater than 0. They are always positive. Now, when you find the inverse of the function, which is logarithmic function, in that case, what happens? Now, let's look into the inverse, which is y equals to log of ax. Now, in inverse of a function, domain and range flips. So what really happens here is that the domain becomes the range of the exponential functions. So domain will be x belonging to real numbers, where x is greater than 0, and the range will be the domain of exponential function. So it will be y belongs to real numbers. As you can clearly see in the graph which has been reflected on the line y equals to x. So we get the graph y equals to log to the base a of x. Perfect. So once again, see how the domain and range are related. So as far as the domain is concerned, it becomes the range for the inverse function, and the range becomes the domain of the inverse function. That makes sense, correct? So this is very important to understand. Now, let's look into the exponential form of logarithmic equation. So if I consider the equation which is log a of x, what we have done here is compare these two. So what we have done here is that base is a, right? A is the base to the power of y. That is how you get this term is equal to x. So that is a way of writing logarithmic and exponential functions. So basically at this stage we are discussing two forms with you. One, we are saying logarithmic form. Let me write here. And the other one is the exponential form. So many times you will notice that when we are working with exponential and logarithmic functions, we are actually switching between the logarithmic and the exponential forms as convenient to us. And that helps to simplify the solution of questions. We'll just see how easy it is. So see, once again, look at the two forms. So the a, the base is base. Do you see the base? A and a are same. So base to the power of y is equal to x. And that is how we kind of link the two forms. Now here are the rules. Log a of 1 is 0. From the graph you can very clearly see that for any value of a which is greater than 0 and not equal to 1, we have seen that log a of 1 is 0, right? So that is the point which signifies this. It's easy. You can write this in exponential form. So write this in exponential form. What do you get? You get 1 equals to a to the power of 0. Makes sense, right? Anything to the power of 0 is 1, and so 1 equals to 1. Perfect. So that is how you could easily kind of correlate it, right? Now here, when we have log a of a is 1, write it in exponential form. So then we can say a is equal to a to the power of 1, which we know is a. And so clearly we have the form given to us. So whenever an equation is given in the logarithmic form, you can always write like this. And here, in this case, which is log to the base a of a to the power of x equals to x, we could always take this a to this side, write it in exponential form, and what we get is a to the power of x is equal to a to the power of x. It is that simple to understand. Perfect. The last one here is a very important equation, and that also comes from the definition itself. So when we are looking into a to the power of log to the base a of x equals to y, think about it like this. Once again, look at the equation. What is a to the power of something? Well, a to the power of y. Do you see this equation written here? Right? A to the power of y is x. So that clearly means that we could write this as y equals to. So from here, we know a to the power of y is equal to x. That means y equals to log to the base a of x. Correct? That is what we have right there. We know y is log to the base a of x. So that is by definition itself. So that is how we actually define our logarithmic function. So I hope from here things are absolutely clear. You could also correlate that the point on the exponential function, which is 0, 1, is getting reflected and on the y equals to 1, and you get it right there. So that is how these points are related. All the points on the log function are basically reflection of the exponential function on y equals to x. Correct? So I hope this part is absolutely clear and you understand how we could correlate the exponential functions and the logarithmic functions. Correct? Now, there are different ways of proving this. we can take alternate ways of proving the same thing in the next part of the video. So again, I'm having the same slide, but this time I will actually give you the proof which could be an alternate way of understanding the proof itself. The important part to prove here is something like this. We could, let's get back to this. We know log to the base a of 1 equals to 0. You know that anything to the power of 1 is what? Anything to the power of 0 is what? Those two things help. We know a to the power of 0 is basically equal to 1, and therefore the point will be that log of 1 is 0, right? And here, you know, a to the power of 1 is equal to a. And converting to logarithmic forms give you the equation itself. So it is a direct relation. So we can, from here, when we know a to the power of 0 is 1, we can always say, in logarithmic form, if I write this, it'll be log to the base a, that is the base, right? Log to the base a of 1 is 0. And in this case, we could write log to the base a of a is 1. So writing in exponential form and then in logarithmic form gives us the result directly as we have just seen here. Correct? Now, the next question is, how do we prove that log to the base a of a to the power of x is x? So we can say let log to the base a to the power of x be t, maybe something else, not x. In that case, what is t? This is what we need to figure out. Perfect. What is t? So that basically, if I write this into the exponential form, we get a to the power of x is a to the power of t. And from here, you can actually connect the exponents. When we have the same base, it means what? It means x is equal to t. Now, since x is equal to t, so we have shown x is t. So that means we have already proved that the identity, which is log to the base a of a to the power of x, is indeed equal to x. Do you see that? So that is how we could also prove it. So these are alternate ways of proving the same thing. Perfect. Now let's take what is a to the power of log ax. Now the last one here, we can say that let it be equal to, let me write down here, log to the base ax as in the exponential form a to the power of t. In that case, we know that t will be log to the base a of x. And that gives you clearly that x is equals to a to the power of t. And so we have once again shown that this x and a to the power of t is one and the same thing. And therefore, we have shown the proof of a to the power of log of ax is equal to x. Correct? So that is how we could actually prove it. Now, let's look into the logs of logarithms. Now we'll focus on laws of logarithm. Now this one, the very first one given here, is log of uv, that is product of 2, is log u plus log v, where product of uv is greater than 0. Then we have the quotient rule, which is log of u over v is log to the base a of u minus log to the base a of v, where the product of u and v is greater than 0. Well, all these laws, the other four also, we will be actually deriving them using a simple substitution and then working with the exponential equations. The substitutions are given to you here. So we'll substitute log to the base a of u as s. In that case, you can always write u as a to the power of s. So let's look into this substitution once again. So we'll substitute log to the base a of u as, let's say, s. In that case, what is u equals to? U will be a to the power of s, correct? The other substitution which we'll do is log to the base a of v is, let us say, t. In that case, v will be equals to a to the power of t. We fairly well know how to work with exponents. So once you convert the log equation into the exponential equation, it becomes easier to work. So that is the strategy. So let us see how to do or derive these particular formulas. So we'll begin with the product rule. So here we have log to the base a of u times v. What is that equal to? We need to prove that this is equal to log to the base a of u plus log to the base a of v. Now it is kind of important to understand the restriction itself. Let's look into this. So here, this part, the argument, we know uv should be greater than 0. So that means that either both are positive or both are negative. So actually, this formula works for both the conditions. And therefore, we have in the formula itself, we are saying log to the base a of uv is log to the base a of absolute value of u. Now it makes sense. If u is negative and v is negative, we have to take the absolute value because log is can only be calculated when the argument itself is greater than 0, right? So that is why the absolute symbol is very important. It is many times skipped since we assume that most of the time only first part will be answered, correct? But in the test questions, you'll find UV both negative given to you. Then the students might sometimes get confused. So it is avoid all that confusion. We have to write absolute symbol. So I hope that makes sense now, right? So that minus V will now become positive. Perfect. This is what we need to prove. Now, as we talked about the substitution, we know that log of AU has been substituted as S. That really means that U is equal to A to the power of S. And we'll also substitute log to the base A of V as, let's say, T. In that case, V can be written as A to the power of T. So the left-hand side in this particular case is log to the base a of u times v. U can be written as a to the power of s and v can be written as a to the power of t. Perfect. Now this could be written as log to the base a of a to the power of s plus t. Right? And what is that equal to? Well, this is equal to just s plus t. Right? We learned earlier the formula, which is the properties of logarithms. Log to the base a of a to the power of x is basically x. So in this particular case, you can see these two a's and x is s plus t. So what we get here is s plus t. Now what is s and what is t? Well, s is log to the base a of u and t is log to the base a of v. Now since both could be negative, right? Both could be negative. It is important to write absolute value since they should be positive. Does make sense to you? And this is what we have on the right hand side. And so we have proved the identity. So you can treat them as identities also. Perfect. Now I think it is simpler to do the next part. So I'd like you to pause the video and prove the quotient identity. So what we just now did is also referred to as product identity. Okay, so let's take the next one, which we'll call as the quotient identity. So we'll now prove the second one, which is the quotient of u and v is difference between the log values of u and v, the absolute u and the absolute v values. Correct? So once again, we'll begin with the substitution, which is we are saying that log to the base a of u is equal to s, and that really means that u is equals to a to the power of s. And we'll also substitute log to the base a of v as t, and that means that v is equals to a to the power of t. And therefore, now let's begin with the left hand side, which is log of u over v. Now we could write this as log of u is basically a to the power of s, and v is a to the power of t. Now this is like quotient, right? So it can be written as log of a to the power of s minus t, and that is equal to s minus t, since we know that, let me write down the rule once again, that log of a to the power of x is actually x. Perfect. Because of that, this is true. So what we have shown here is that the left hand side is equals to s minus t, but s is log to the base a of u, and we'll take the absolute value since u can be negative, and we have difference between this and the absolute value of v. Perfect. So that is how you actually prove it. Is that clear to you? So that's simple. This substitution really helps to answer all these questions. So next one also we'll use the same substitution and do the needful. So now we have the next question, which is log to the base a of u to the power of n can be written as n times log to the base a of u. This is also treated as a power rule, right? So we have log to the base a of u to the power of n equals to n times log to the base a of u. Now in this case again we are going to do the same substitution, which is right there. So we'll substitute that log to the base a of u, let it be s, and that really means that u is equals to a to the power of s. Now let us substitute the left hand side, which is log to the base a of u to the power of n. So we can write this as log to the base a, u is a to the power of s. So a to the power of s to the power of n. And that really means it could be written using this power rule, log to the base a of a to the power of Sn, right? Product of S and n, and this is the product of S and n. Now that means S is what? Well, S is log to the base a u, right? So we'll just write this as S as log to the base a of u, and that is n, right? So it could be written as n times log to the base a of u. So that is how we are going to prove this identity. Perfect. This is what was required, and that is the right hand side. So in this case, definitely u has to be greater than 0, right? So in this particular case, u is greater than 0. Only then the log is valid. Perfect. Now let's take the next one, which is this time we are going to do the second part, which is a very special case. Now we can do it in two ways. We could use the formula which we just derived. So log of base a of 1 over v can be written as log to the base a of v to the power of minus 1. And now, utilizing this particular property, which is the power rule, we can write down that this is equal to minus 1 that comes here, log to the base a of v. And that is what we wanted to show. Clear? Now there is another way also to prove this. We'll call this as alternate method. Now you could think about expanding this using the sum and difference rule. So we can have log to the base a of 1 over v as equals to log to the base a of 1 minus log to the base a of v. Now anything log for 1 is 0. So we get 0 minus log to the base a of v, and that gives you minus log to the base a of v. And remember, in this, v has to be greater than 0. In the other one, the value of u should be greater than 0. Perfect. So there are two different ways of proving this particular identity. Now here is a very important understanding of this particular rule. So when you say that the logarithm of 1 over v is negative, it means what? Let's look into the graph of logarithm. The graph of logarithm is kind of like this, right? So what you notice here is that this portion is negative, and that is what we are trying to say. Correct? So you will notice that if v is greater than 0, in that case 1 over v is between 0 1 over v is between 0 and 1, correct? So it is between this point. And in that case, log of 1 over v is negative. Do you see that? So this negative part specifies that if the value of v is in that region, then we have a negative value of log. So that could be at times a communication question. I hope you're getting the concept. So we could ask this question in many different ways. We have shown two ways of proving, and the other thing is that we need to show that if v is greater than 0, in that case, the graph of the function is negative when v is between 0 to 1, right? So I should have written this as when v is between, not 1 over v, right? When v is between 0 and 1. So in this case, between 0 and 1, what you get is a negative value, correct? Okay. Now let's look into the question on change of base. So what we have here is log to the base a of x is equal to log to the base b of x divided by log to the base b of a. This is called change of base formula. So we are changing the base from a to b, right? So this is a general formula, and we could actually use this to change the base to 10, change the base to e, or anything else, whatever is relevant in a particular situation. Perfect. So that is the key to this. Now, let us say that log to the base a of x is, let us say, t. In that case, x will be equal to a to the power of t. Perfect. Now let us consider log to the base b of x. Now since x is given to us as a to the power of t, I could always write this as log to the base b of a to the power of t. Now that really means that I could write this as t times log to the base b of a, right? So that means that we have written log to the base b of x as t times. And what is t? Well, the value of t can be substituted from here. And so what we get here is log to the base a of x. And we already have here log to the base b of a. And now you can isolate log to the base a of x. And what do you get? You get the ratio of log to the base b of x divided by log to the base b of a. So that is how we can prove the identity. And that is called change of base formula as shown here. Perfect. So now I would like you to take the other part as an exercise. So now try to show that log to the base a of b is 1 over log to the base b of a, right? You can pause the video and do that. Here is the solution. We have already shown that log to the base a of x is log to the base a of, we are changing to b, so let me write this as b, any other base, b of x over log to the base b of a. So notice what kind of changes are we doing here. So this part here, x, is right in the numerator, and this part a is right there when you are changing the base from a to b. Perfect. Now let's look into the question and see how to do it. So that means that if I have log to the base a of b and I want to change this base to b, I'll write this as log to the base b of b over log to the base b of a. And what is the numerator part? It is just 1, right? So we get 1 over log to the base b of a. Since we know that log to the base b of b is 1, and therefore we get this 1 here. And we get a result which is log to the base a of b is 1 over log to the base b of a. So do you see how the base and the argument changes in this case, right? So that is a very, very important formula. Many times we are going to use it. Now I'm going to take up in the next video an exercise on applications of the formulas derived here. So we'll begin with some basic equations, convert those exponential equations to logarithmic equations. We'll see how to combine the logs, and we'll see how to solve word problems with logarithms using these properties. I'd like you to go through this set once again, understand the concepts, as these concepts of proving will help you solve problems also. I hope it makes sense. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.